Good day, everybody, and once again we are back together. All right, so today we are looking at the physical science chemistry paper 2 exam for 2023. And so if you haven't subscribed, please just make sure you are part of this family. And of course, you can always reach us. Our email address is info@mlungisiNkosi.co.za. For anything that you need in terms of maths and science. And by the way, we also have a center in Honeydew in Johannesburg. You're welcome to come through to our center. All right, let's get into this question paper. Right, I'm going to start with the multiple choice section and let's delve right into it. Okay, so they say for which one of the following molecular formulae are chain isomers possible? Right, so if I look at this, C4H10, yes, that is absolutely possible because you can get methyl propane, which has 4 carbons. So definitely this would be possible. Let's see if there's no other answer that kind of looks like it. Okay, so the other one is 3 carbons, 2 and 3. Nah, the other one's definitely not possible. All right, so they say which one of the following compounds has the lowest vapor pressure under the same conditions? Right, now remember that vapor pressure, right, is a function of, the strength of intermolecular forces, right? So the greater the intermolecular strength, the lower the vapor pressure. All right, so if I look at this, the strongest intermolecular force would have to be D, right? It's a carboxylic acid because not only does it have hydrogen bonds, right, but it has 2 sides of hydrogen bonds, unlike the the alcohol, which also has a hydrogen bond. So we're going to go with D. Right, and the next one, they say the type of organic compound formed when a haloalkane is heated in the presence of a concentrated strong base, right? So remember, when we take concentrated strong base, in this case, we're going to form an elimination reaction. And so what happens with that haloalkane is that it will form an alkene. So B would be the correct answer there. Okay, so the next question, they say excess hydrochloric acid of concentration 0.1 mole reacts with 2 grams of magnesium under different conditions, right? They say which one of the following combinations of conditions will produce the largest volume of hydrogen in the first minute. So essentially what they are asking us, which one will have the highest rate of reaction, right? So essentially, if we look at this, we've got powder and 20 degrees Celsius. Okay, so yes, that will have a great rate of reaction. But I see I've got powder there, which means I'm not only changing the state of division, but I'm also increasing the temperature. So in this case, definitely C would be the correct answer. All right, let's go to the next question. They say the potential energy diagram for a chemical reaction is shown below. Right, they say which one of the following combinations is correct for the forward reaction. Right, let's see. So delta H, remember that delta H will be the energy of the products, right? The potential energy of the products minus the reactant. So that will be X minus Y, right? So the only possible answers would be C and D. And then we know that for activation energy, we always take the energy for the forward reaction. It will be the energy of the activated complex minus the one for the energy of the reactant. So that will be Z minus Y. Okay, so with that said, there's only one possible answer there, and that is definitely C. And definitely Z would be the potential energy of the activated complex. All right, let's go to the next question. They say consider the following reactions that reach equilibrium in a beaker. Right, now they say to us a few drops of concentrated sodium hydroxide are now added to the beaker. Now remember, the moment that I add sodium hydroxide, what does it contribute? It will give me hydroxide ions, and those hydroxide ions tend to react with hydronium ions, right, to form H2O. So in that case, what are we actually doing? We are decreasing the concentration of hydronium ions, right? And so what will happen if we decrease that concentration, right? We will favor the reverse reaction so that it tries to replace the hydronium ions. So they say, which one of the following combinations correctly identifies the disturbance on the system, right, and the system's response, right? So the disturbance that we made, as we said, we decreased the concentration of hydronium ions, right? So which one? Okay, both of these. So A or B. And in this case, we said that the reverse reaction will be favored. So the correct answer there, according to Le Chatelier's principle, right, will be B. Next question. So they say, according to the Lowry-Bronsted theory, a conjugate base is formed when, okay, so remember, if we're taking a conjugate base, we will form a conjugate base when an acid, right, donates its proton. Okay, so in this case, when an acid donates its proton, it gives rise to a conjugate base, right? So in this case, the correct answer there, they say a proton is removed from an acid. That's option C, right? So that is really how we answer that question. Now they say consider the statement below regarding an alkali substance. Firstly, they say an alkaline substance reacts with an acid to form a neutral solution. Okay, I would believe that statement. Of course, if they are in the right measures, right, in that case, they will neutralize each other. Okay, the next one says turns red litmus blue. Definitely. When we put an alkaline solution, red litmus turns blue. Okay, so you'd have to know that, right? And the third one says forms a salt when it reacts with an acid. Well, that is also true. In that case, that is what happens when an acid reacts with an alkaline substance. They say which of the following statements are true? I will definitely take 1, 2, and 3. Okay, right. So the next one, they say to us, consider the cell notation of a galvanic cell. Which one of the following equations represents the half reaction taking place at the positive electrode? Now, at the positive electrode, remember for a galvanic cell, we know that the positive electrode is the cathode. Remember the anode? This is the one that gives away electrons, right? This is where oxidation takes place. So in this case, it would be negative. So as a result, we know the cathode is positive. And as a result, in this case, ladies and gents, so which means when I give you a cell notation, remember what's on the right-hand side is our cathode, right? And so as a result, it means that we are taking silver ions and they're going to undergo reduction and form silver Ag, right? So in this case, the correct reaction would actually be A. All right, and finally for 1.10, they say we've got a concentrated solution of sodium chloride that undergoes electrolysis. They say which one of the combination correctly shows the product formed at each electrode. So remember, when we've got sodium chloride, what we're going to form there, we're going to have sodium plus and Cl minus chloride ions, right? So what happens? We know that the sodium ions will go to, in this case, will undergo oxidation at the negative electrode, right? And the chloride ions will form chlorine, right? But this is at the positive electrode, okay? And we know in this case, what are we doing? We're undergoing oxidation, in this case for sodium, right? That's the actually, sorry, that will undergo reduction rather. Okay, it will gain electrons and therefore become sodium. Okay, right. And this, remember, wherever we are undergoing reduction, right, that is the cathode. Okay, so that's the cathode. So that will be our anode. We are undergoing oxidation there. Cl minus ions give away electrons and therefore become chlorine, right? So we'll see chlorine gas forming over there. Right, so the correct answer there should be on the anode, we are forming chlorine, definitely. And on the cathode, we are forming sodium. So I'm going to take this answer over here. Well, it makes a heart. So that's how we leave this part of the question. All right, and let's go on to question 2. Okay, let's go into question 2. They say study the table below and answer the questions that follow. They say define the term unsaturated hydrocarbon. Remember, these are hydrocarbons that have 2 or more bonds around each carbon atoms, right? All right, so let's go to question 2.2.1. They say write down the letter that represents the unsaturated hydrocarbon. So which one would be the unsaturated hydrocarbon? Well, it would definitely be D in this case. I can see that between those two carbons, there isn't a maximum number of hydrogens. So definitely that would be compound D. Okay, so I'll write that one there. So that's compound D. And then they say the IUPAC name of compound A. If I look at compound A, now please be very, very careful, ladies and gents. Our longest chain here is going to be this one over here. That's the longest chain that we've got, right? So now, if I look at it, how many carbons do I have and where will I start numbering? Well, I think it's much easier, or rather, it would give us a lower combination if we start from the right, because my first side chain is actually at carbon number 3 from the left, okay, from there. So I'm going to start from the right. So that's 1, 2, 3, 4, this is 5, and 6. And now I can see at carbon number 2, as well as at carbon number 4, I've got side chains of methyl each, right? With 1 carbon, so that's methyl. So this is going to be 2, 4, right? So that's 2, 4, dimethyl. Don't forget the hyphen, right? The dash. Okay, dimethyl. And in this case, I've got single bonds on my parent chain and with 6 carbons, right? So this is going to be hexane. Hope that makes sense, ladies and gents. Right, the next question says, write down the IUPAC name of the positional isomer of compound B. Now let's go and look at compound B. Compound B is an alcohol, right? And it has this hydroxide ion at carbon number 1, right? So we want the IUPAC name. So this is going to be 1-propanol. So its positional isomer would simply be 2-propanol, or you can say propan-2-ol. So whichever way that you want to write that. So that would be propan-2-ol, or you can say this is 2-propanol. Okay, right. So 2.2.4 says the IUPAC name of compound D. Right, so if I look at compound D, if you look at it, ladies and gents, so we've got CH3, then we've got CH2s. How many of them? 4 of them. CH2. Okay, I'm going to try and write it. CH2, CH2, CH2. So we've got 4 of those CH2s. And then we've got a CH, right? Now that can only be because there's a double bond in between, right? So double bond with that CH2. Right, now how many carbons do we have? We've got, okay, let's count them. So we're going to start numbering from the right. So that's 1, 2, 3, 4, 5, 6, and 7. So that will be 7 carbons, right? Between carbon number 1 and 2, we've got a double bond there, right? And so that will become, all right, so 7 carbons, that's hept. So this is going to be hept 2, hept 1. Remember, that's between carbon number 1 and 2. So this is going to be hept 1. We always take the smaller number, right? So that's going to be hept 1 in. Okay, so let's go to the next question. They say write down a balanced equation using molecular formulae for the combustion of compound A. So compound A, if you remember, that was all right, it was that 2,4 dimethyl. So the molecular formula, it has 8 carbons, so it would be C8, right? So this would be C8 H18, right? You can check it's an alkane, and this would be plus oxygen, and you'd get carbon dioxide and water. But remember, we still need to balance this out, right? So 8 carbons on the left, we'll put 8 on the right, 18 hydrogens on the left. Okay, so to make that 18, we have to put a 9 there, right? Which means the number of oxygens, so that's 8 times 2 on the right-hand side, which is 16, and 9 times 1, which is 9, and 16 plus 9 would give us 25. So this would be 25 over 2, right? On the left-hand side. So if you haven't seen me do this, please go and watch my videos on organic chemistry, right? Reactions as well, right? So now you can never have a fraction there as your number of moles. So in this case, what I'm going to do is multiply everything by 2. So therefore that number changes. Okay, so 2 times 1 here will give me 2. 25 over 2 times 2 will give me 25. 8 times 2 will give me 16. And 9 times 2 will give me 18. And please remember, in that case, then it means that my reaction is perfectly balanced. Okay, right, and let's go to the next question. So they say to us the molecular the formula rather C4H8O represents 2 compounds that are positional isomers of each other. Right, so if I look at this, that can either be a carboxylic acid or it can be an aldehyde, right? So they say define the term functional isomers. We say these are organic compounds with the same molecular formula, right? So remember, the molecular formula is the same. Okay, molecular formula. All right. But in this case, belong to 2 different functional groups, or you can say that they've got different, they belong to 2 different homologous series. Okay, or you can even say that they belong, yes, that they come from different function, they rather have 2 different functional groups. Okay, right. So they say write down the structural formula, the structural formulae of each of these 2 functional isomers. So we need the structure of them, right? I don't have enough space. So what I'll do, I'll just go to that guy there. Okay, I'll write it over there. So it would be C4, H8 and O. So it would be 4 carbons, right? The last one, or rather the aldehyde, would look like this. Okay, so the one would be an aldehyde, the other one would be a ketone, right? So that's C4. Okay, we've got, right, so there we go. We've got the number of hydrogens there, so that's the aldehyde. The other one is a ketone, and what would that ketone look like? Right, so ketones, remember, have got the double bond O anywhere else but the terminal carbons, right? So they do not have hydrogens at the carbon that is at the end. Okay, so there we go. Right, so that's C4, H8, and O. So that is the, so that would be an aldehyde, the first one, right? And the second one would be a ketone. Right, so let's go to the next one. They say a 2-gram sample of compound E contains 1.09 grams of carbon and 0.18 grams of hydrogen. The molecular mass of compound E is 88 grams per mole. And they say determine the molecular formula of compound E by means of a calculation. So what I'm going to do is, let me just deal with them individually, right? So I'm just going to have different columns for each of the compounds. Now, if we look at compound E, right, it has carbon, hydrogen, and oxygen. So we'll have carbon here, we'll have hydrogen there, and we'll have oxygen. So we know the mass of carbon is 1.09. The mass of hydrogen is 0.18, right? So which means the mass of oxygen will be 2 grams minus the 2. So let's just calculate it there. That would be 2 minus the 1.09 minus the 0.18. Okay, so that gives us 0.73. So which means oxygen is 0.73. Now what we're going to do is, let's divide each of the masses by the molar mass of each. Right? Remember, the molar mass of carbon is 12. The molar mass of hydrogen is 1. The molar mass of oxygen is 16. Right? So what do I get there? So I'll say 1.09 divided by 12. I get 0.09. Okay, 0.18 divided by 1 will give me 0.18. And oxygen, that's 0.73 divided by 16. That will give me 0.045, right? Okay, we can say 0.046. All right, so there we go. So what we do is, ladies and gents, we identify which one is the smallest of those numbers, right? I can see it is 0.09. So I'm going to divide each one of them by 0.09 so that it gives me the empirical formula. So divide by 0.09 and divide that by 0.09. Okay, so what number do we get there? So for the first one, quite clearly, it will give me 1. For the second one, it will give me 2. I believe it will give me 2, right? So 0.18 divided by 0.09, that does definitely give us 2. And for oxygen, 0.046 divided by 0.09, that gives me 0.5. Okay, let's just approximate that to 0.5. Okay, right, and in this case, what do we get? 0.05 of that guy. All right, now, so which means if I'm going to look at this compound, it would be C1, right, H2, and 0.5 of oxygen, right? But remember, in this case, I can't have empirical formula as a decimal, right? So let's rather multiply everything by 2. So in this case, that will give me C2H4 and O, right? So that's what I will have. 0.5 times 2 will give me 1, right? Now, they have also given me the molecular formula of the compound. Now, if we try and calculate there, okay, I know I don't have enough space. I'm just going to write it in the other page, but I'll remove the stuff. So if I calculate the the molecular formula of what I have there, 2 carbons, so this will be 2 times 12, right, plus 4 hydrogens, that's 4 times 1, plus 16, right? So let's check. So 2 times 12 gives me 24, right, plus the, okay, so plus the 16 gives me 40, plus the 4 gives me 44. So I get 44 grams per mole, right? But note the one that is given to us is 88 grams per mole, right? So which means we need to multiply everything by 2 already from what I have, right? It means it's twice as big. So therefore, right, the molecular formula of this compound will be C4H8O2. That is how we will get the molecular compound formula rather of that compound. I hope that makes sense, ladies and gents, right? Even if we had to spill over to the next one, let's jump into question 3. Learners, investigate the boiling points of the 4 organic compounds given, right? So they say that we've got butanone, we've got butane 1-ol, we've got propanoic acid, and we've got 2-methyl propane 1-ol. Their molecular masses are more or less the same, right? But except for butanone, right? But it's almost there. They say define the term boiling point. Please remember your definitions, ladies and gents. We say that this is a temperature, right, where the vapor pressure of a compound is equal to the molecular, the atmospheric pressure, right? Okay, so let's go to the next question. They say which compound, butane 1-ol or 2-methyl propane 1-ol, will have the higher boiling point? Explain fully, right? Right, so in this case, butane 1-ol and 2-methyl propane. So first of all, we know which one will have a higher boiling point. It should definitely be butane 1-ol, right? It will be butane 1-ol. And now how are we going to explain that? Right, so first of all, we are going to explain that butane 1-ol, so butane 1-ol is linear with a greater surface area, right? With a greater surface area. So remember that, when we've got surface area is a big determining factor. Sorry, I wanted to write greater there, right? Is a very big determining factor in the strength of intermolecular forces, right? And what do we know about 2-methyl propane 1-ol? So 2-methyl propane 1-ol, okay, is more spherical, right, with lower surface area. 2-methyl propane 1-ol. Okay, so we said is spherical. So in this case, it has side chains. So it therefore becomes more spherical with lower surface area. So with lower surface area, right? And what do we note? So lower surface area. Okay. So what do we note? Right? As surface area, right? Or rather, the strength of intermolecular forces increases with an increase in surface area. Okay, so I'm just going to say that, ladies and gents, and you'll write it down. Okay, so therefore, more energy is required to separate the molecules of butane 1-ol than those of 2-methyl propane 1-ol, right? So remember to state the difference between the two, okay, and to state that we know that surface area, okay, or strength of intermolecular forces, or this time we can say the strength of London forces, right, will increase with an increase in surface area. And so in this case, we will have butane 1-ol with greater boiling point. All right, so they give us those curves. So let me try and just remove that stuff there. Okay, so they give us those curves there. They say we've got P, Q, R, and S. All right, so we need to find out who's who in the zoo, right? Okay, if I were you, let's start doing that now. Probably the questions would actually ask us to do that. Okay, we'll come back to that. We'll come back. Okay, they say which physical property is represented by temperature X. Okay, so where is temperature X there? Right, so in this case, we note there that temperature X, they said to us the curves P, Q, R, and S were obtained from the result of the investigation, right? X represents a specific temperature, all right? Now, what I would say there is that this temperature X is actually what we call the boiling point. The next question, they say, which curve P, Q, R, and S represent? Okay, as I did say, right, we should have actually just found out who's who in the zoo. Right, so if we go back there, I want you to note which one has the highest boiling point in this particular mix, right? So definitely propanoic acid for me would definitely have the highest. So I would say P, that's going to be propanoic acid. Please, it doesn't mean that P stands for propanoic. Okay, it just is a letter. Okay, and then the next one, so this would be the first one, this would be P. And then which one comes immediately under that? All right, so if I look at it, I'm going to say definitely it's going to be butane 1-ol, right? So this would be Q, okay? Because remember, both of them have got hydrogen bonds, which are the highest intermolecular forces in terms of strength. So, and then after that, but remember the difference between alcohols and acids is that acids have got two sides of hydrogen bonds, right? And then after that, I would definitely say 2-methyl propane 1-ol. It is still an alcohol, so it does have that hydrogen bond. So it means that would be R, and definitely S would be butanone, because that has got dipole forces, right? In addition to your London forces, right? So they said to us, which curve represents butanone? All right, so let's go back to our diagram there. Butanone, that would be S. All right, and they say propanoic acid, we said that was P. And we said 2-methyl propane 1-ol, so we said that was R. Okay, so that's curve R. Hope you understood the reasons there. They say give a reason for the answer to 3.4.2. Okay, why did we choose propanoic acid? All right, because propanoic acid has got 2 sites, right, of hydrogen bonding. Okay, which is the strongest intermolecular force in this case, right? And essentially that is how this cookie crumbles, right? We're going to go into question 4. They say to us the flow diagram below represents different organic reactions. PQ and R are organic compounds. Right, so let's first have a look at it. So what happens? Compound Q reacts with bromine and we get 1,2 dibromo, right? So notice that both of those bromines were actually added. So that does tell me that compound Q must have been an alkene, all right? And in that case, it does simply tell us that we must have had methyl propene, right? And in that case, compound reaction 2, we would take that alkene and we react it with hydrochloric acid. Okay, so we know in that case that we are going to actually form another addition reaction. Okay, and we're going to form a haloalkane, right? And if we take that haloalkane to form an alcohol in reaction 3, we would have to have taken that through a reaction with sodium hydroxide, right? Dilute sodium hydroxide in that case. Right, so let's get right into the questions. They say the type of addition reaction. So they say for reaction 1, that is, write down the type of addition reaction. So we acknowledge it is an addition reaction. So that means it's an unsaturated hydrocarbon, right? So we added bromine. That would be bromination. Or you can say this is halogenation. Right, we added a halogen. So in that case, that would be a halogenation. They say one observable change which occurs in the container during this reaction. So remember that bromine is brown in color, but once it reacts, okay, the brown color disappears. So we'll say the bromine color let's rather say fades. Okay, right, so they say the structural formula of compound Q. So note, we simply just added the bromos there, right? So we had the methyl, we had the prop, but we had propene in this case. So that means we had something that looks like this. Okay, the methyl over there. Okay, so we've got this guy, but with a double bond. All right, so there we go. So this is what okay, that's supposed to be a hydrogen. Okay, so this is what our structure. Oh, I'm missing just one hydrogen over there. Yeah, I think the rest is fine. Okay, so this is what the structural formula of compound Q would actually look like. Next question, they say reaction 2, they say write down the IUPAC name of compound R. Okay, so if we take that reaction, so we would have added, would break that double bond, okay, and we are now going to add, according to Markovnikov's rule, we are going to now add chlorine. Now remember, we'll add the chlorine where we've got the a lower number of hydrogens. So the chlorine will go to number 2 and the hydrogen will go to number 1. Okay, so if you look at that, so this will be 2-chloro, okay, 2-methyl propane. So I'm going to say this is going to be 2-chloro. Remember Markovnikov's rule? 2, okay, so that's 2-methyl. Apologies for writing over that. Propane. I couldn't fit it to make it one word. I wrote it underneath, but you do get the idea, right? So 2-chloro, 2-methyl propane. And let's go to reaction 3. They say a balanced equation, write down rather, a balanced equation using structural formulae for the organic compounds. Okay, so for reaction 3, what happens in reaction 3? We are going to take that guy there, the 2-chloro, 2-methyl propane, and they said we need to write a balanced reaction, right? Okay, using structural formulae. Okay, so this will be just slightly tedious. Okay, remember we had the 2-methyl propane over there. And please, guys, don't leave out the hydrogens, right? So we're going to now react this. Oh, sorry, I forgot the chlorine there. So that's going to be H, H, and H. Now, remember, we are reacting it with sodium hydroxide. That's what we said, right? Okay, let me just check there. A balanced equation using structural formulae. Yes, for the organic compounds. All right, so then we're going to react this with sodium hydroxide, right? And what do we form over there? We are now going to, remember we said we're going to form an alcohol. So which means the hydroxide ion will now replace the Cl minus, the Cl, right? So the product there, and I'm going to try and squeeze it, so I'm going to write it over here. So the product there would be exactly the same thing, right? Except now I'm going to replace the hydrogens, the chlorine, with the OH. Okay, so there we go. And right, so what would be the byproduct that we form? Okay, so in that case, that means that we are going to also form, remember you've got the sodium and the chloride that's still left there, so that would be plus the sodium chloride. And you can also indicate that this is in the presence of mild heat. Okay, right, so there we go for that reaction. I hope that you could understand that, even though it was difficult to really try to write it down. Okay, let's go to the next question. Okay, so we have a reaction, or rather they said to us the IUPAC name of the alcohol. So what alcohol did we form? So we've got an OH at carbon number 2. So this would be 2-methyl. Okay, so this would be 2-methyl. This would be propane. Okay, that's 3 carbons. And at carbon number 2, we've got an OL. So this is 2-methyl propane 2-ol. Right, now let's go to reaction 4 rather. They say reaction 4 is an elimination reaction, and they want us to write down the type of elimination reaction that it is. Right, so note there, we're taking that alcohol and we are taking it back to becoming an alkene. Right, you remember we said compound Q was an alkene. So in that case, we are actually removing the H and the OH, so that would be dehydration, right? And please remember, every time that you've got an alcohol, an elimination, we always start with that D. So that is dehydration reaction, okay? Right, so, and then they say to us, butane 1-ol reacts with propanoic acid, right, in the presence of a catalyst. And then they say write down the reaction that takes place, the type of reaction rather that takes place. Well, an alcohol and a carboxylic acid, so that always is esterification. Okay, so we are forming esters there. And the last question says the IUPAC name of the organic product formed. So remember, we start by naming. So with esters, we're going to always name the alcohol first, right? So we're going to say this is going to be butyl, okay? and this is going to be propanoate. So that would be butyl propanoate. That would be the alcohol, the ester that is formed. All right, ladies and gents, and would have gotten ourselves 18 marks. This section, guys, please just maximize as much as possible. And then now we're going to go into rates of reactions. They say consider the following decomposition reaction that takes place in a sealed 2 cubic decimeter container. Okay, so we've got dinitrogen pentaoxide, okay, that decomposes to form nitrogen dioxide plus oxygen. They say the graph shows how the concentrations of dinitrogen pentaoxide and nitrogen dioxide change with time. All right, so definitely you can tell that decreasing graph would be dinitrogen pentaoxide, because I'm expecting that the amount or the concentration of it will decrease with time, whereas the one that is increasing would definitely be of the products that are formed, right? So now they say refer to the graph above and give a reason why curve A represents the change in concentration of nitrogen dioxide. Exactly what we said, right? Products will tend to increase with time, or you can say that because nitrogen dioxide is a product, okay, so therefore it will increase as the reaction proceeds. Okay, is a product. Okay, so you can complete that statement there. They say consider the statement below. The rate of decomposition of dinitrogen pentaoxide is half the rate of formation of nitrogen dioxide. Is this statement true or false? And we need to give a reason for our answer. Now let's go back to the reaction. They said the rate, okay, so when you take the rate of any reaction, right? So the rate of reaction would be equal to the change in the concentration, right, of anything divided by the change in time. So in this case, if I look at it, whatever nitrogen dioxide does, right, for every mole or 2 moles that I use, right, of nitrogen dinitrogen pentaoxide, I get 4 moles. So I get twice as much of this, right? So for any single amount of change that occurs here, I get double the amount of change over there, right? So if that is the case, then it means that that statement is definitely true, right? So I will say definitely that statement is true, right? So in this case, because they said give a reason for your answer, right? We will say the number of moles, okay? Or we will say rather the ratio, let's say the ratio of nitrogen dioxide is twice that of dinitrogen pentaoxide, right? In the reaction. All right, so let's go to that. I think that should suffice, but of course you can find other ways of expressing exactly the same thing. So they say to us, calculate the mass of nitrogen dioxide present in the container at 400 seconds. All right, so let's go there. Okay, remember nitrogen dioxide was actually the graph A. So I see at 400 seconds how much nitrogen dioxide has been formed. We started from 0, right, at time 0, and at 400 seconds we now have formed a concentration of 200, but please don't forget to say times 10 minus 4, right? So that's the amount that I have. So the concentration Okay, and what did they want? They want the mass. So concentration, that's mass over the molar mass times the volume, right? So let's try and find that out there. So we know what we are simply going to do. We've got the concentration, and if you don't mind, I'm just going to write it on here. So the concentration is 200 times 10 minus 4. We want the mass. Now the molar mass, that's nitrogen dioxide. So the molar mass of nitrogen, that's 14, right, on the periodic table. And that of oxygen is 16, but you've got two oxygens, right? So that would be 14 plus 32, right? 16 times 2, that will give us 32, right? So that will be 46. So the molar mass is 46 multiplied by the volume, all right? So did they give us the volume? They said we've got a 2 cubic decimeter container. So in this case, that means that our volume is 2. Okay, so to get the mass, we would just simply multiply those out. So this would be 200 exponent negative 4, okay, multiplied by 46, right? We're going to cross multiply, multiplied by 2. And so the mass that we get is 1.84 grams that has been formed after 400 seconds. Right, I hope that makes sense, ladies and gents. Okay, so they say the next one, the average rate of production of oxygen in moles per cubic decimeters per second. All right, now the volume, they said in 700 seconds, right? So if I look at this, I had not been given anything on oxygen, but I have been given the amount in terms of nitrogen dioxide. So let's check at 700 seconds. So this would be right there at the end of the reaction, right? So how much is the amount? Okay, so I'm going to take my ruler, right? So how much is the amount of nitrogen dioxide that has been formed there? So you can see it's sitting over there, right? So we know that our division per line, so that would be 5, because if you notice there, we've got 50 between our major divisions. So in that case, so this would be 50, all right, and you divide it by the number of lines in between. So each one, so that's 10 lines in between there. So 50 divided by 10 would give us 5, right? So if you look at that there, so we've got 250, right? So that's how many lines? That's 1, 2, 3, 4, 5, and 6, right? So that would be for every 2, there's an addition of 10. So that would be 260, 270, and that's 280. Okay, so the amount of nitrogen dioxide that has been formed, all right, the concentration is 280. But now remember, ladies and gents, all of this happens within the same container, so the volume would actually be the same. So I can use concentration in this case, in terms of their ratios, right? So they said they wanted in concentration, right, per second. So I will say for every 4 nitrogen dioxide, I get 1 oxygen. That's what the ratio says there, right? For every 4, I get 1. So the question is, if I've got 280, okay, remember this guy is 280 times 10 minus 4, how much oxygen am I going to get? Okay, so in that case, let's cross multiply. I'm looking for the concentration of oxygen, right? So that would be 4 times x. You can imagine that's going to be a quarter of that. Divide by 4, right? is equals to 280 times 10 minus 4. Divide both sides by 4. Then that will give me the concentration. So that will be the concentration of oxygen, right? So 280 divided by 4, that will give me 70 times 10 minus 4. That's in moles per cubic decimeters, right? Now note, ladies and gents, I've got now the concentration of oxygen. So to calculate the rate, right? So the rate of that reaction, they said in concentration divided by seconds. So I'll take that 70, right? So that would be 70 minus 0, 70 times 10 minus 4 rather, minus 4, minus 0, right? We would have started with nothing. And for the time, we know this happened in 700 seconds, right? Minus 0. And so what does that give us? Okay, so I'm going to say, you could have also calculated the rate of nitrogen dioxide and divide that by 4. So that would be 70 exponent negative 4, right, divided by 700 seconds. Okay, so they said per second, and that would give me 0 point, okay, let's convert that into, so that would be 1 times 10 minus 5, right? That's moles per cubic decimeters per second. All right, so that would be the rate of that reaction. And sorry guys that I had to squeeze this in somehow, right? Unfortunately, that's the nature in which I'm answering this. Actually, we had some more space here. I could have used that space. Okay, so they said the initial concentration of nitrogen dinitrogen pentaoxide is now decreased. Okay, now they say to us, redraw the distribution curve right above in your answer book and label this curve P. All right, so what would happen? We'd actually get almost exactly the same curve, except we're expecting less number of moles, okay? So that means that we are going to have something that looks, I'm going to just draw it in a different color, in the blue, okay? So I'm going to get, right, so the peak would be exactly at the same time. The only difference is that the number of particles, right, would be less. All right, so this would be graph Q. That's what they said, redraw, label it as P. They say on the same set of axes, sorry, I forgot to read the question. The same set of axes, sketch the graph that will be obtained with a higher concentration. Look at this, I didn't even read the question. They say with a higher concentration of dinitrogen pentaoxide, right, label this curve as Q. All right, so now if we had a higher concentration, right, of dinitrogen, so that means, as I said, we would have exactly the same. Okay, let me do this. Okay, so you would have a graph that looks like this. So the graphs would peak exactly at the same time, but it's just that, so our graph Q would have more moles in that case, and because the concentration is much higher. Right, so the final question, they say, will the rate of decomposition of dinitrogen pentaoxide at higher concentration be higher than, lower than, or equal to the original rate of decomposition? It will definitely be higher than, okay? Right, they say explain using the collision theory. Now, please remember, and that's why even the graph looks like that, right? An increase in concentration, okay, increase in concentration will increase the number of particles per unit volume, right? So we have now more particles per unit volume. Okay. Now that means that more particles, more particles will have sufficient kinetic energy and correct orientation, right? And correct orientation. Sorry that my handwriting is a bit terrible there, right? And that means that will increase the number of collisions, effective collisions per second. So that will result in an increase in the number of collisions per second. And thus the rate of reaction will increase. All right, so in this case, collisions per second, and the rate of reaction increases. Right, so that is really how the cookie crumbles, ladies and gents. And would have earned ourselves a good 16 marks there. Right, and let's go into the next part of the questions. Question number 6 rather. They say 1 mole of pure hydrogen iodide is sealed in a 1 cubic decimeter container at 723.21 Kelvin. Equilibrium is reached according to the following balanced equation. Now, ladies and gents, please remember in this case, you need to calm down, right? We know we are going to have some calculations on Kc, right? Now, they say to us it is found that we've got 0.11 moles of iodine, right, present at equilibrium. Okay, so let's try to... Okay, so they say state Le Chatelier's principle, right? You can state it in the way that is comfortable for you, right? In a closed system, okay, if one of the factors that affect equilibrium changes, then the equilibrium will oppose the change and a new equilibrium will be established. Of course, there are many ways of skinning that cat. Okay, so you can choose one of them. Right, they say determine the number of moles of each of the following at equilibrium. Right, so, all right. So first of all, the number of moles of hydrogen at equilibrium. So we needed to actually just draw that table for ourselves. In fact, let's do exactly that. Okay, so what I'm going to do is I'm going to just draw a little bit of a table there. Right. And I know that some of you prefer to always have that part about ratios. I never really include it, but if you want it, you can actually. You're more than welcome to do so. So we're going to have initial. Okay, this is in moles. This is going to be change. That's in moles. That's going to be equilibrium. Please note you're not wasting time when you're filling this part in. Okay, so this will be equilibrium concentration, right? And that's in moles per cubic decimeters. Okay, right. So what do we have on our reaction? We've got 2Hi and we've got hydrogen and we've got I2. Now remember, what did they say to us? They said 1 mole of pure hydrogen gas, right? Rather 1 mole of pure hydrogen iodide gas, right? Was sealed. So in this case, we had 1 mole of this guy. They said nothing about hydrogen and iodine at in the beginning, right? Because they were products, so we assume that we started with nothing. Okay, right, we found that we've got 0.11 moles of iodine, right, at equilibrium. So we got 0.11 moles. So that means in this case, how much did we produce? We must have produced 0.11, right? And now note, in this case, it must also mean, right, because you've got a 1:1 ratio, right, between hydrogen and iodine, right? So what does that mean? If I formed 0.11 there, that would also be the same ratio, 0.11. And that simply means that for hydrogen iodide, that would be twice, right? So that would be 0.22, twice the amount of iodine that you got. And please note, ladies and gents, that you only use the ratios in this portion of your table, right? You do not use ratios, and that's why I've marked it in red so that you can remember that. Once you get one of them, you can use the ratios to determine the other portions. Right, now, in this case, we know that the amount there would be 0.11. And what about hydrogen iodide? Remember, that is a reactant, so that means 1 minus the 0.22 because we used hydrogen iodide. So that will be 0.78, right? And of course, we can calculate the concentrations there. We'll come back to that. Now, they said determine the number of moles of each of the following at equilibrium. So hydrogen, right, that would be 0.11. Okay, so that's 0.11 moles. What about hydrogen iodide? That would be 0.78 at equilibrium. They said at equilibrium, right? So in that case, hydrogen iodide, that's what, actually that's exactly what we said, 0.78. Okay, so that's 0.78 moles. Right, so now they say the equilibrium constant Kc at 421, right, Kelvin is 0.02. Okay, now they say to us the temperature of the container is now increased. So remember, the moment we increase temperature, we would automatically also increase the Kc, we will change rather the Kc value. And what I notice here is that our Kc value moves from 0.02 to becoming 0.09. So that tells me that the Kc value increased, and so it means we must have favored the forward reaction, right? Okay, so now they are asking us a question. Is the forward reaction exothermic or endothermic? All right, now please note what happened. We increased temperature, and as a result, the Kc value increased. So which means more products were formed with an increase in temperature, so which means that we favored the forward reaction. What that simply means is that the forward reaction must be endothermic, right? So remember that an increase in temperature will always favor the endothermic reaction. All right, so they said fully explain your answer, right? So we will say an increase in temperature favors the endothermic reaction. Increase in temperature, right, favors endothermic reaction. All right, and we'll note in this case that the forward reaction was favored. The forward reaction was favored. And how do we note that? Because of the increased Kc, right? So the forward reaction was favored, judging by the increase in Kc. Okay, increase in Kc. All right, and so therefore the forward reaction is endothermic. All right, endothermic. So I'm just going to write it there. Right, okay. Sorry about those spillages. Okay, let's go to the next portion of this question. Right, so we said we've explained in according to the Le Chatelier's principle there. Now they say calculate the mass of hydrogen iodide present at the new equilibrium at 850 Kelvin. All right, now ladies and gents, so at the old equilibrium, please, I want you to just try to follow in what I'm doing, right? So what did we do? So we found out that the amount or the Kc value, right, initially was 0.02, okay? So now they say to us the temperature of the container is now increased. And we find that the Kc value changes. All right. Now, please, I want you to note. So what do we note? It means that we must have formed more products, right? So what I'm going to do, let's do this. So this I'm going to treat as my old Kc, right? Now, please, I want you to listen very carefully. All right. So let me just continue the table. And I'm going to say, right, so I'm going to treat these as my initial amounts, right? And now there was another change that took place. Okay, so in this case, I'm going to have a new equilibrium. And please, I want you guys to listen very carefully, right? So there we are. So now I note there was a change that took place when we increased temperature. Now, if suppose I say to you that the amount of, let's say, iodine changed by X, all right? So the amount of iodine changed by X, how much would the amount of hydrogen change by? Remember, the ratio is 1:1, so that means it would also change by X. And so, which means that the amount of hydrogen iodide would have changed by 2x. And I know that I favored the forward reaction. So how much do I have at equilibrium? I've got now, right, I started with 0.78. I used 2x, so this would be 0.78 minus 2x. And I started with 0.11, I used x, so this will be 0.11 minus x. And what would be the amount of, this would be plus x. Remember that I form hydrogen, right? And what would be this one? This would also be 0.11 plus x. Okay? So this would be the new equilibrium amounts. Okay, and now I know that now I need to calculate the concentrations for these amounts. And when you get the concentration, remember, it's number of moles divided by the volume. And what was our volume in this case? Our volume was 1, right? So if you divide anything by 1, you still get the very same value. So our equilibrium concentration, which is in moles per cubic decimeters, would give us 0.78 minus 2x. This would give us 0.11 plus x, and this would be 0.11 plus x as well, right? Now, let's do this. Let's go and do the calculation. Right, so we're going to look for the, we're going to look for the value of x, and that value of x will give us now the mass of hydrogen iodide at the new equilibrium, right? So I'm going to say Kc, the molar concentration of my products, right? What's my products? It's going to be H2. It is a gas, so I'm going to add it into my formula, divided by, right, multiplied by I2, right, both of them raised to the exponent 1 because that's the ratio. This is divided by Hi, but remember the concentration there, right, then the ratio is 2, so that will mean that we square that. Remember, this is equal to 0.01. So now let's, 0.09, which is the Kc value, right? So we're given that Kc value to be 0.09. So I've got 0.09, okay, which is equal to 0.11 plus x, okay, times another 0.11 plus x, which is squared, right? So I'm taking this times that and I square it, right? So which means it's that squared, divided by 0.78 minus 2x, okay, squared, right? So remember we said we're squaring that. And so what I'm going to do, ladies and gents, I'm going to just simply take the square root on both sides, right? I've got a square and a square there, and so I'm just going to take the square root on both sides. So now if I take the square root on both sides, the squares cancel, right? And the square root of 0.09 will be 0.3, right? Okay, so the square root of 0.09 gives me 0.3. So I've got now, we're going to do just a little bit of mathematical gymnastics, right? So I've got 0.11 plus x divided by 0.78 minus 2x, right? This is over 1. And then we can cross multiply. Okay, if we cross multiply, we've got 0.3 into 0.78. Okay, ladies and gents, just for the sake of time, I'm just going to multiply those in. So 0.3 times 0.78, that gives me 0.234, right? Minus 0.3 times negative 2 will give me minus 0.6x, right? I'm sure you can see that. And this is equal to 0.11 plus x. And then now let's try and get everything onto one side. So I am going to take the 0.6x to the other side. That gives me 1.6x. And I'm going to take the 0.11 onto that side. 0.234 minus 0.11. I've got 0.124. And then I'm going to divide this by 1.6. Okay, so x gives me 0.0775. Now, ladies and gents, let's bring this to some closure. What are we looking for? We are looking for the mass, right, of hydrogen iodide present at the new equilibrium. So we're looking for the mass for this here. So firstly, the number of moles will be 0.11 plus the x. So that will be 0.11 plus 0.00775. Okay. I'm going to add 0.11. Please, you can verify if this is correct. So that's 0.1875 moles. Now to get the mass, okay, right? So I am going to say mass is number of moles multiplied by the molar mass. So this will be 0.1875 multiplied by the molar mass of hydrogen iodide. Okay, let's quickly go and check our periodic table, right? So our periodic table, what's the molar mass for hydrogen, for iodine rather? There we go, it's 127, right? And for hydrogen, we know it is always going to be 1, right? So if we take that, okay, we're gonna go back there, right? Let's try and go back there, right? So we're going to say number of moles times, so it's 1 plus 127, which gives us 128. Okay, so the mass of that will be, oh, I actually just removed the, so that's 1875, right? This is multiplied by 128. And so the mass at equilibrium will be 24 grams, Right, I hope that you were able to follow on, ladies and gents. You can rewind this and watch again, all right, if it does assist. But otherwise, that is how we're going to answer question 8. I hope question 6 rather. All right, so let's go to the next portion. Jump into question 7. Let's go to it. We say the conductivity of 3 acid solutions, A, B, and C, as shown below, is investigated at the same temperature. And they give us those acids there: sulfuric acid, nitric acid, and that is ethanoic acid. So they say the brightness of the bulb in the apparatus shown below is used as a measure of the conductivity of the solution. So they say the acid solutions are electrolytes, right? Now they say define the term electrolyte. So remember that an electrolyte is a solution that conducts electricity, okay, through the formation of ions. Okay, so they say the brightness of the bulb for each of the solution is compared. Right, in which solutions, A or B, will the bulb be brighter? Give a reason for the answer by referring to the type of acids. Right, so if we compare A and B, note that sulfuric acid is remember we say that this is a diprotic acid. Okay, so remember it's able to donate 2, so therefore it will contribute more ions in this case. Right, so they're both strong acids, but because sulfuric acid is a diprotic acid, so in that case it will burn brighter in bulb A. Right, they say give a reason for the answer by referring to the type of acids. Right, we've just said that. We said sulfuric acid, okay, H2SO4 is a diprotic acid. Okay, so diprotic acid, and therefore will contribute more ions than a nitric acid. And then they say in which solution, B or C, will the bulb be brighter? Give a reason for the answer by referring to the type of acids. Right, so note in this case between B and C, we're taking a strong acid as well and a weak acid. Okay, so strong acids, remember they ionize completely, right, in solution, whereas weak acids ionize partially. So definitely the answer there will be B, right, because nitric acid is a strong acid, Okay, and it ionizes completely. Right, so you can mention all of that, or you can mention the fact that ethanoic acid is a weak acid, right, and so it ionizes partially, so it will not have as many ions as nitric acid will have. Right, so let's go to the next part of the question. They say we've got a hydrochloric acid solution, right, which is standardized by titrating it against 25 cubic centimeters, right, so they've given us there, of a 0.04 moles per cubic decimeter sodium carbonate solution, right. At the end point, it is found that 19.5 cubic centimeters of hydrochloric acid has reacted. Right, now they give us the balanced reaction there. They said calculate the concentration of hydrochloric acid. Now remember, we are talking about neutralization here, or we are talking about a titration, so which means we can use our famous formula, right? So that's CAVA over CBVB, which is NA over NB. Right, so if we substitute there, concentration of the acid is what we are looking for, right? That's what they asked us. So I'm going to leave it as A. So this is going to be, okay, so that's B and that would be A, right? So concentration of A multiplied by volume of A. So they said we used 19.5, and I can keep it in the same units for as long as the other one is in the same units as well, right? Concentration of the base, they said this is 0.04 multiplied by the volume. So this is 25. And now note, ladies and gents, when it comes to Na, so that's 2. It's that coefficient there. So that will be 2. And B has got 1 over there. And we can do our mathematical gymnastics. So what I'll do is multiply 0.04 times 25 times 2. 0.04 times 25 times 2. Okay, that gives me 2 there. And I will divide that by 19.5. Okay, so I get the concentration of the acid to be 0.1, let's just say 0.1 moles per cubic decimeters, right? Okay, so that's 0.1 moles per cubic decimeters. Right, and that is how we'll go about that question. Right, now they say suppose that a few drops of water were present in the burette before it was filled with the hydrochloric acid solution. Right, they say how will the volume of hydrochloric acid needed to reach the end point be affected? Now, if there were a few drops of water, that would actually lower the concentration of sodium carbonate, okay? So what would happen there is that we would actually need more acid to, we'd need less acid rather to neutralize. So it would affect the reading quite a bit. So they say how will that affect, or rather how will the volume of the hydrochloric acid solution needed to reach the endpoint be affected? All right, so definitely that volume would, okay, so that means the concentration there is lower. Okay, so we'd need a bigger volume. Okay, so that would mean that the volume would be greater than, okay, and we've just given that that reason, right, that would lower the concentration of hydrochloric acid, and as a result it means that a bigger volume would be necessary in order to neutralize. Okay, right, so we go to the next portion. Right, I'm gonna have to make some space here so that we find at least where we can answer that question. Right, so they say to us a concentrated household product, right, ChemClean, contains ammonia as the main cleaning agent. To determine the amount of ammonia present in 1 cubic decimeters of ChemClean, the following procedure is followed. They say 20 cubic centimeters of ChemClean is added to 250 cubic centimeter flask. The flask is then filled rather to the 250 cubic centimeter mark with distilled water. So they are diluting this solution of ChemClean, right? So now they say that the diluted solution is titrated against a hydrochloric acid solution of the concentration as calculated in 7.2.1. Okay, so which means 0.1 moles per cubic decimeters, right? So we know the concentration of the acid, and then they say during the titration, 22 cubic centimeters of the diluted ChemClean solution is neutralized by 18.7 cubic centimeters of hydrochloric acid, right? The balance reaction for the equation rather for the reaction is shown below, right? So now I want us to note, ladies and gents, so that is the reaction that took place. And what I like is that it's a 1-to-1 reaction. So we can find out the number of moles. So that's where I'm going to start. Let's find out the number of moles of hydrochloric acid that we actually used in that neutralization reaction, right? And I'm going to just stay with me for now, right? So that's number of moles, that will be concentration times volume, right? So that will be 0.1. Remember, they said the same concentration as we had calculated. And the volume that we used for hydrochloric acid was 18.7, right? So remember, when we use this formula, we're going to have to use volume in cubic decimeters. So we're going to divide that 18.7 by 1,000, right? So if I say 18.7 divided by 1,000, okay, so that will give me 0.0187. Right, apologies for that. Right, so 0.1 multiplied by, so remember we said 18.7, we divided that by 1,000, right? That gave us 0.0187. And so we multiply that by 0.1, that will give us 0.00, right? 187 moles. So these are the moles of hydrochloric acid that were used during that titration. Now, I want us to note, so therefore it means if the reaction is a 1-to-1 reaction, therefore the number of moles of NH3 that reacted with that acid would be exactly the same, 0.00187 moles, right? Because it's a 1:1 ratio, so we can place that there because it's a 1-to-1 ratio. But not only do we know that, ladies and gents, now we know the number of moles that were in that solution, right? Now we also know, I want you to please note, we also know the volume of the solution that reacted. So we can find out the concentration, and please, I want you to follow me in this. We can find the concentration of the diluted ChemClean. So now concentration, right, of ChemClean, right, this is going to be number of moles divided by volume. So this gives me, okay, let's use that there. So number of moles, that's what I just calculated, 0.00187 divided by the volume of ChemClean was 22 cubic centimeters. So that's 22 divided by 1,000 again, right? So that will give us 0.022. Now let's find out the concentration. Okay, so we'll say that value there, 0.0187, right, divided by 0.0, that's 0.00187, that's divided by 0.022, okay, and that gives us 0.085. So the concentration of ChemClean, ladies and gents, right, so concentration for ChemClean, right, but this is the diluted amount, okay, would be equal to that amount, 0.085. Okay, 85 moles per cubic decimeters. Okay, right, now ladies and gents, I want you to note this is the diluted ChemClean that came from this. Now I'm going to write it on to the other side. Now remember, I always make an example with Oros, right? If you're not South African, that's a diluted, orange concentrate, right? And what we do is we pour water into it. So if you make a mixture of Oros and I pour it into a glass, whatever is in that glass tastes exactly the same as what is inside, let's say, whatever it is that you are mixing it into, let's say a jug, for instance, right? So what am I trying to say? The concentration that I would have had here would be the same as the concentration I have in the jug, right? So therefore, remember I took a small amount, 22 cubic centimeters, but where did I take it from? I took it from this guy, okay? So that means that the concentration of ChemClean that was diluted is actually 0.085 moles per cubic decimeters. I hope that makes sense, ladies and gents. Right, now, which means I can find out the concentration, right, of the concentrated ChemClean. Right, how am I going to do that? So I'm going to say, right, C1, V1, so this is the original, the concentrated one, is equal to C2, V2, this is the dilute one, okay? So I want the concentration of the original, right, the one that I used from there, okay? And the volume of it was 20 cubic centimeters, right? But I know the concentration of the diluted form, which is 0.085. And how much of it was there? It was 250, right? So 250. And so to get the original concentration, I'll just divide that by 20 there. And what is the original concentration? So now I am going to say, right, 0.085 multiplied by 250, okay, and I divide that by 20. Right, so the original concentration of ChemClean, ladies and gents, is 1.0625 moles per cubic decimeters. Right, I hope that you've been following and you really understand this, right? So the original ChemClean concentration was 1.065. And where does this come from? It comes from there, right? Okay, we took a small sample of it, and now we were looking for the mass, right, of ammonia in that 1 cubic decimeters, right? And remember, ammonia is the one that has been reacting all along, right? So which means that was the concentration of ammonia. So all I'm going to do is say number of moles, that's concentration times the volume, and that will give us the number of moles. And so I'll say the number of moles, the concentration 1.0625 multiplied by the volume, which is 1, okay? And in this case, right, what am I going to get? I am going to get exactly the same number, right, which is going to be 1.0, okay, well, we can say 1.06, right? So number of moles would be 1.06 moles of ammonia in that ChemClean solution. Right, so I will leave it there, ladies and gents, and I hope that you were able to follow and understand, right? Finally, they say, will the pH of the solution at the end of the titration be greater than, equal to, or less than, right? They say write down the relevant equation as motivation for the answer, okay? Now, what did we do in this case? We took NH3, right, ChemClean, right? And we are now going to react it with the acid, right? And what does the acid do? Of course, it will neutralize that. So the pH should be, all right, so it is going to be less than, right? So let's see, will the pH of the solution at the end of the titration rather be greater than, equal to, or less than, oh sorry, they said at the end of the titration. So in that case, we took a weak acid and we took a weak base rather, and we took a strong acid. So which means that we are going to form an acidic salt, right? So that means that our pH has to be less than 7. Now, they say write down the relevant equation to prove this, okay? So remember that we formed NH4 plus Cl, right? Which is our, the salt that we would form in that case. But I want you to note, if we take NH4, right? So how do we prove this? We use, in this case, the hydrolysis of salts. So NH4Cl plus H2O, right? What is this guy going to form? It's going to form NH3, right? But note, plus H3O plus. So because of the presence of the hydronium ions, in this case, that will become an acidic solution at the end. Right, I hope that we understood that, ladies and gents. I know question 7.2.3 is quite a lengthy one, but please try to watch it again if you must, just to understand it. Before I continue, I realized I left out the mass there. They asked for the mass of ammonia, but I only calculated up until the number of moles. So to get the mass, we would say mass is number of moles multiplied by molar mass. Actually, we could have used concentration as mass over molar mass times volume. So in this case, because I'm looking for the mass, that would be 1.06. Okay, and that's multiplied by, now remember, nitrogen is 14, and you've got 3 hydrogens, so that's 14 plus 3 times 1, that will give you 17. And if I multiply that, okay, I still had that amount there, so I'm just simply going to, okay, let's take that unsigned multiplied by 17. Okay, all right, now something is fishy there. Okay, so let's take 1.0625 and multiply that by 17. We get 18.06 grams. So that's 18.06 grams of ammonia. All right, apologies, I had omitted that there. All right, so we can go to the next question. So question 8 says, learners want to identify an unknown metal X using a standard cell X and X2 plus. They set up an electrochemical cell under standard conditions using 2 half cells as shown in the diagram below. They say the initial EMF of the cell is 1.2. And note, they are saying initial because remember, this cell does reach equilibrium at some point. Okay, so the first question, they say state the standard conditions under which the cell functions. So what are the standard conditions of the cell? Is that first of all, the initial concentration of our electrolytes, okay, must be equal to 1 mole per cubic decimeters, and the temperature must be equal to 25 degrees Celsius, right? That's room temperature. But because one of your electrodes is a gas, we have to also mention pressure. Okay, so that the pressure of the gas, right, that is used must be equal to 1 atmosphere, or you can say 100 kilopascals. All right, so that those are the 3 standard conditions in this case. Now they say state one function of component Y, that's the salt bridge. So remember we said that the salt bridge neutralizes excess ions. Okay, excess ions. And that it completes the circuit. So you can say it completes the circuit. Okay. All right. So those are the two functions. Right, so they say after the cell has operated for some time, it is found that the mass of electrode X has increased. Now, what does that mean? It must mean that electrode X is the one that is undergoing reduction, okay? So which means the gain of electrons takes place there. So I would say, therefore, means electrons must be moving in that direction, right? So they say identify by means of a suitable calculation, right? Identify X rather by means of a suitable calculation. So we're going to say E cell, right? And please remember to write the equation as it appears. So E standard for the cathode minus the E standard for the anode. So we've already identified, right? Our EMF of the cell is 1.2, right? We did say that X is undergoing reduction. So remember, reduction occurs at the cathode, right? Remember, we spoke about red cat. Okay, so this is going to be E cathode. We don't know what it is. Okay, standard. Minus E anode. Now remember, it means that hydrogen is the anode, and if you go and check in your table, you'll see that hydrogen has got a potential of 0, right? So which means that our cathode must have a standard potential of positive 1.2 volts. Now let's go and visit our table, right, and see there which one has got positive 1.2. Let's see. Okay, there we go. All right. So which means that X must be platinum. Okay, so that means that we've got platinum there as our electrode. So that means that X is platinum. Right, so let's go to the next one. Okay, they say write down the oxidation half reaction that takes place in the cell. Now remember, oxidation, that's the loss of electrons that happens at the anode, right? So this means that now this guy is going to be our anode, right? Okay. X is platinum, and the anode is hydrogen in this case. So remember, for hydrogen to undergo the loss of electrons, right, I want you to please note, let's go back to our standard reduction potential table, right? So there is the standard hydrogen reaction, so which means it's actually undergoing the reverse of that reaction. So H2 loses electrons, okay? So we're going to say H2. So what that reaction looks like is H2, please with one arrow, would be 2H plus by giving away 2 electrons, right? Please, very important for that arrow to be in one direction. Right, so in this case, the next question, they say half cell X is now replaced with AU, right, and AU3 half cell. The initial EMF of the cell is now 1.5 volts. As the cell operates, the AU electrode increases in mass. All right, so which means AU will also undergo, just like platinum, it would also undergo reduction. But what that simply means is that, now remember, you still have the hydrogen half cell, right? So what that simply means is that in that case, it would actually undergo a reduction as well, just like platinum did, but it gives us a higher EMF value, all right? Now they say to us, arrange the oxidizing agents, X2 plus, AU3 plus, and H in order of increasing strength. Now note strength of oxidizing agent. Now remember, right? Strength of oxidizing agent, it means that I'm arranging it in terms of their reduction potentials, right? So now I want you to note, right? So which one underwent reduction? Okay, so I know it's going to be X2 plus, AU2 plus, and in this case H plus, right, was the one that underwent oxidation, right? So in terms of oxidizing agents, right, so they said increasing strength, right? So which means from the lowest in terms of strength, oxidizing agents, right, to the one with the highest. Okay, so again, please remember, so this one underwent oxidation. So in this case, it means that hydrogen would be the lowest in terms of oxidizing agents, right? So that will be H, sorry, H plus, right? And then remember that we then had X2 that gave us a potential of 1.2. So in terms of the strength, definitely PT2 plus would be the one that follows. And then finally, it would be AU3 plus. Okay, right. So in this case, they say fully explain. So, right. So note, first of all, H2, right, rather it's the one that lost electrons to both, right? So loses electrons to both. Okay, that's why it's the weakest. Okay, so loses electrons to both PT and AU, right? And then I noticed that the reduction potential of PT, right, is less than that of AU, right? So in terms of their reduction potential, the reduction potential of PT2 plus, or rather let me say PT2 plus half cell, right, should be less than, was less than the one for AU2 plus, AU3 plus, right? And so in that case, that is why we'd say AU3 plus is the one with the highest strength in terms of oxidizing agents, right? And in decreasing order like that, or in increasing order. When we go to the right, okay, and now we've got only one more question to go, and that is it, ladies and gents. Question 9, they say the simplified electrolytic cell below is used to electroplate a metal spring. Zinc nitrate is used as an electrode, and R is an electrode as well. They said zinc nitrate rather is used as an electrolyte, okay, and R is the electrode. They say define the term electrolytic cell. So remember, an electrolytic cell is a cell that converts electrical energy into chemical energy. Right, they say which electrode, R or metal spring, is the anode, and give a reason for the answer. All right, so definitely I would say, right, so remember anode, this is where oxidation takes place, the loss of electrons. So definitely that should be at metal R or electrode R. Right, and why should that be the case? That oxidation must take place there. Oxidation takes place. All right, and the next part, they say write down the equation for the half reaction occurring at the metal spring, right? So remember, this is electroplating. So what we are trying to do is electroplate that spring with what? With zinc, right? Whatever electrolyte we use there, we must use a similar metal electrode for it. So this would be electroplating with zinc. So therefore, at the metal spring, we'll have a reaction Zn2 plus, right, undergoing reduction, right, the zinc ions, and therefore forming zinc. So this guy will be covered with zinc. All right, so, and they say name or formula of a suitable metal that can be used as electrode R. Well, we've just said that. That would definitely be zinc. And then they say explain the answer to question 9.3.2. All right, so in this case, zinc ions, all right, would have to be replaced. Would be, in fact, we can say would undergo oxidation. Would undergo oxidation. Okay, to replace the ones reduced in the electrolyte, right? In the electrolyte. All right, ladies and gents, and really that is how this question paper ends, right? I hope that you were able to follow on and that you really understood it. I've tried my best to simplify it, but please, if you want to get in touch with us, our email address is info@mlungisinkosi.co.za. You can also visit our center, which is in Honeydew in Johannesburg. We've got great things for you there. Visit our website also, mlungisinkosi.co.za. All right. Otherwise, from me, your favorite uncle, I will see you guys again next time. Sharp, sharp.